Hi, in this video I'm going to be talking about generational adversarial networks, or GANs. So the format of this video, first I want to go over what GANs are and how they're used. Then I'm going to be looking at the specifics of how this project is set up in terms of the models used in the datasets. And then I want to do a code walkthrough of just an implementation of a GAN algorithm. So what GANs are, first the end goal of a GAN network is to train a generator model to be able to emulate or produce data that is similar to data from a data set. So we're not trying to produce specific instances of that data set, but rather we're trying to find common themes within that data set and kind of be able to produce a fake entry in that data set. So the generator will take noise as its input and then ideally output data that is indistinguishable from that data set. So GANs incorporate two networks. There's this generator, which is kind of our final output, but there's also this discriminator network, separate discriminator network, and its job is to classify real and fake images from each other. So that's where the whole adversarial portion of the name comes from, is that you'll have this generator network producing fakes and the discriminator network filtering them. And you put these two networks at odds with one another for however many training sessions that you want, and eventually you have your output. So these are generally used for image generation at the moment. I don't think that there's any other big commercial uses. So producing just like fake images of people, places. I think that they can also be used for upscaling somehow. But yeah, just a quick overview on how the training actually works. The discriminator training is pretty standard for machine learning. You'll have either entries from your true data set, you'll have entries from your true data set, or so true entries from your data set as an input, and you'll be training those against true labels, and then you bring in an equal amount of entries from your generator, and you're training that against false labels. For the generator, it's a little different. We'll be taking noise, that's your input from the generator, and you propagate that all the way through. So that goes through the generator, then gets past the discriminator. That gets trained on true labels, or so you're calculating the loss on true labels by propagating that all the way through and updating your generator. So we'll take a look at exactly how that works in the code walkthrough, but that'll do for now. Let's take a look at the project folder here. So this is some of the end results that I got here. I trained on a celebrity data set. I trained models on a flower data set, and I trained models on a dog data set. So and I trained some different types of models. This was the first model that I had on the celebrity data set. These images don't look that much better upscaled. They're 64 by 64, so we can just look at it within the folder here. And you can see, I mean, I think that I could tell that these are not real people, but at the same time you can see that elements of the face, that the network has learned elements of the faces. You can see eyes, you can see a nose and a mouth and a general head shape. The flower ones look kind of pretty, so you can use these for like fake art, or is it fake art? And then we also have a different celebrity data set generator here. What's kind of interesting is the variance that you can get on these. So these are, these were both trained for 10,000 cycles or whatever, and but it was two different models, so you would expect different results. But it's kind of interesting what the consistencies between samples from a given data set. So these ones all kind of have like a dark bluish background and brownish background, whereas these ones have kind of like a pasty yellowy browny face. I don't know. The dogs one didn't turn out that great, to be honest. These were some of the better sample images that I had, where I could like vaguely see an outline of a dog. But I think that with a dog's data set, there's just like so much kind of variance within photos. All of the celebrity photos have a face front and center, so the model is able to figure out, oh, like I need facial features in the middle of the photo. Kind of same thing with the flowers, but with pictures of dogs, it's just kind of too random. There's close-ups of dogs and dogs in the distance and blah 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 blah. And then there's another flowers one here. I don't know which one's prettier. I think this one. So apart from that, so those are some of the sample output images that I have. So some of the models that I use, this is where the models are saved. These are the model structures here in this folder. So this project was done using PyTorch, so all of these are PyTorch kind of standard NN modules, meaning that they implement, you just have kind of the layers that you're using here, and then you have this forward function that actually defines how the data is handled. So our x is our input, and then the x goes through the convolution layer, in this case goes through this convolution layer, and then a batch normalization layer, and then our ReLU function does that a couple times until the data is the appropriate size, and then you return your final data. So that's what these look like. I based this off a PyTorch tutorial, so I think that this one is very close or exactly the same as what was used in the PyTorch tutorial. And then I also used kind of a residual variation on these, so I have these like residual layers that kind of get bypassed through it won't go through the convolutional one, but instead it will go through this upsampling function and a channel pooling function to match the final dimensions, and then get added back as a residual layer, or like as a skip connection. So yeah, I guess I'll move on from the models. We can take a look at this pipeline here. So I have there's not too much going on in this file. I have a weights initialization function. This is our main training function here. And then a sample function to produce samples from an already trained model, and a preview true to preview actual true instances from a data set. We should talk about data sets. So here are the data sets that I have. These data sets were generated by the celebrity one was downloaded from a zip, but the rest were on this site, I think called ImageSenseNet or something along those lines. I'll link it in the description. But it has this handy way to generate these sort of text files containing links to a set of images. So this one's beverages. I haven't trained a beverage model, but that's how I got the flowers one. That's how I got the dogs one. And then I have a data function to get all those photos and add them to a folder. And also, I have, yes, that's the image from URLs here. And I have a image loader, which is what I'm using as a generator to serve data in the pipeline, which we can get to now. So here's our train function. This is where our actual training algorithm takes place. So we're loading in a couple of things here. We're loading in the generator model that we want to use. We're loading in the discriminator model that we want to use. We're loading in our load image folder, so data.load image folder that takes a given folder, so specifying a data set, and then it's just returning images from that data set with a couple functions applied to them. So you can see I've got like a resize to make sure the images are a certain size. What else are we passing? The batch size, the training steps. I have an update thing that gives you kind of an update on the loss, and the model name. Alright, so going through train, first we're loading our generator neural network. So this is the model, an instance of these. So we'll be loading a generator, and we'll be loading a discriminator. You can either create a new one, and it does this weights initialization function in all of the layers, or you can load a pre-existing one, and it activates that. We have our optimizers, we're just using Atom, and I had success with this learning rate for the amount of training steps that I was doing. Some labels. So the true labels, because this is for the discriminator, where we're classifying or we're using these as our training target data. So when we pass it a real image from the data set, we're training it against a true label. And then when we're training the discriminator on generated or data that was created by the generator, we're going to be passing it the false labels, or the zeros. True data gen, what is this? Oh, this is the generator that we passed in through here to actually fetch real instances of the true data. So after we have that, these are just things. These are some lists that help with the updates that I mentioned earlier. So every X cycles, or every n cycles, it will give kind of an output of the discriminator loss and the generator loss, and also keep track of it for a final graph in the end. Okay, so I'm just going to step through a training cycle here. First thing we have, we're going to land here at the top. So for I in range training steps, the first thing we're doing is we're going to be loading some true data. So this is a real instance from our data set. We're using the celebrity database. So let's see who we got. This is a way to preview it. I don't know who that is. There's like so many celebrities. I took a look through the folder briefly and I didn't recognize most of them. But what we're going to be doing with this, so our next, we're here now, or we just completed this line. So we reset the gradients in our discriminator. We're in our first cycle here, so where there was no gradient to reset. But what that does, every time we call these backward functions, we're calculating gradients, which sort of indicates how we're going to be updating our weights on a neural net. But the way that these networks interplay with one another, we need to reset there because we're going to be setting our gradients when we're actually training our generator. I'll describe that when we get there. But we just reset our gradients. What we're doing here is we're passing into our discriminator our true data. So we're passing, we're getting our predictions from our discriminator. We pass these predictions and we're comparing them to the true labels. So these are our predictions of our untrained discriminator. So ideally we would want these all to be 1s or close to 1s. Our true labels is just a tensor filled with 1s of the same size. And we're calculating our loss based on that. So our loss, and then we are going backward, and now our discriminator is filled with a set of gradients that we got by training against our true labels. What comes next is we do the same thing because our discriminator needs to be trained on true and false data. So we're going to be generating some false data here. So we're generating noise first off. This is our input to our generator, and we're using our generated data. So this is one of our fake images. Right now, since our generator is untrained, I could preview that, but it wouldn't be, obviously it wouldn't be anything close to a real image, or a real instance of celebrity. This function is very similar to what we're doing here. We're passing into our discriminator our generated data, and we're getting our generator discriminator out predictions. So these are the ones that ideally we would want to be false, and we're comparing those against our false labels. So if we look at these, we have a similar set of predictions from our discriminator using the generated data. And then our false labels is just a tensor filled with zeros. We use that to get our generator loss, and then we're back propagating that similarly to how we did before. So that's one iteration of our and then we're finally stepping with our discriminator optimizer and kind of like executing on those gradients and updating our discriminator values. So that's one iteration of how the discriminator is trained. Now we're going to be training our generator. So the generator, it follows a bit of a similar process to what we just did there, actually. We're generating some noise. We use that noise as input as our generator to generate another set of generated data. Here, we're resetting our generator gradients. So generator discriminator out, we put that generated data through the discriminator. And then this time we're calculating our loss on our fake data against true labels. So what we're doing this time is what we ultimately want to do here is update our generator so our output more closely matches true labels, and that our discriminator is more likely to classify our generated data as true. So that's what we have here. And then we're getting that loss backward all the way back through the generator function, so that the gradients are actually being calculated on the discriminator and on the generator, but we're only updating the generator, so that's why this 0 grad is important here. Back at the top. Now we've trained our generator, and then these are some of the loss update. This has nothing to do with training all this stuff down here. This is just some stuff to kind of give an update on the metrics of the models. So you can see that I have this list where I'm appending the loss, and then I think that I'm calculating an average and giving the average loss over that period, kind of like a rolling average. And yeah, so that's the algorithm. Hopefully that makes sense. At the end, there's a plot that gives an output. I think that I'll cut here and then come back in at the end of a session and we can see what that output looks like. Okay, so I ran a set of models for 1,000 cycles. Here's a sample of the output that we get. So here's our pie plot that was generated. We have our generator loss over the 1,000 cycles on here. And then we have our discriminator loss. So you can see our generator did better towards the end, whereas our discriminator stayed mostly consistent. One thing to note about these loss values is that they're kind of treated differently than loss values for other machine learning applications, in that you're sort of chasing a moving target. Like if both your models are improving sort of at the same rate, then your loss will stay the same despite the fact that your models are in fact improving and becoming more useful. So I'm not totally sure what to make of loss values in GAN applications, but here's a set also here the loss values that I mentioned earlier. So that's pretty much it, all I have for the video. I'll post the source code and then the links to generate data sets below the video. Yeah, thanks for watching.